Hello everyone, we're going to be going over section 5.2, which is integer exponents and the quotient rule. So we have four objectives today. We want to use 0 as an exponent, we want to use negative numbers as exponents, we want to use the quotient rule for exponents, we want to use combinations of the rules for exponents. So objective 1, we want to use 0 as an exponent. The power rules are also valid for a 0 exponent. This means that if we have something like 6 to the power of 0 times 6 to the power of 2 is equal to 1 times 6 to the power of 2, which is equal to 6 to the power of 2. Or we can just use our product rule to say 6 to the power of 0 times 6 to the power of 2 is equal to 6 to the power of 0 plus 2, which is equal to 6 to the power of 2. So our 0 exponent states that for any non-zero real number a to the power of 0 is equal to 1, with an example that 17 to the power of 0 is equal to 1. So anything to the power of 0 is just going to be equal to 1. A word of caution, negative a to the power of 0 can be written as negative a to the power of 0, where a to the power of 0 is inside parentheses, which is equal to negative 1, while negative a in parentheses to the power of 0 is equal to positive 1. So you really have to pay attention once again to where the negative is going to be. If the negative is inside your parentheses, it's equal to positive 1. If your negative is outside, or if there are no parentheses, then it'll be equal to negative 1. Now objective 2. We want to use negative numbers as exponents. So we only worked with positive numbers for our product rule and our power rules A through C. So now we want to introduce negative numbers as exponents. So we can see from this list that we have here over to the left-hand side, we have 2 to the power of 2 is 4, 2 to the power of 1 is 2, 2 to the power of 0 is 1. But now 2 to the power of negative 1 is 1 over 2, 2 to the power of negative 2 is 1 over 4, and we can assume that this is going to continue on. So from this list, we generalize that 2 to the power of negative n should be equal to 1 divided by 2 to the power of n. So the product rule is valid for negative exponential expressions as well. So now our product rule will work. Where if we have 6 to the power of negative 2 times 6 to the power of 2, this can be simplified to 6 to the power of negative 2 plus 2, which is equal to 6 to the power of 0, which is 1. So in this case, 6 to the power of negative 2 behaves as the reciprocal of 6 to the power of 2, since their product is going to be 1. Thus, the reciprocal of a to the power of n can be written as 1 divided by a to the power of n. So our negative exponents, we can state that for any non-zero real number a and any integer n, a to the power of negative n is equal to 1 divided by a to the power of n. So for an example, 3 to the power of negative 2 is the same as saying 1 divided by 3 to the power of positive 2, which we can simplify to be 1 over 9. So when we have negative exponents, this does not indicate that our number will be negative. The negative exponent only indicates that we're now going to have the reciprocal of what we had, which is going to be something like a to the power of negative n can be rewritten as 1 divided by a to the power of n. So a negative exponent does not mean a negative answer. We can also change the base to its reciprocal if we also change the sign of the exponent. So if we rewrite our base, say our base is 6, if we change the base to its reciprocal, we can change the sign of the exponent. So if we have 6 to the power of negative 2, that can also be the same as saying 1 divided by 6, all to the power of positive 2. So if you use the reciprocal, you can change your exponent to be a positive. So example 1, we want to write with positive exponents and then simplify. So the expression we're given is 2 divided by 5 is equal to negative 3. Well, we can use the fact that we just learned that we can change the base to its reciprocal if we also change the sign. And we want to work with a positive sign, so we can use the reciprocal of our base. And the reciprocal of our base, remember, if we have a fraction, we're just going to switch the numerator and the denominator. So its reciprocal will be 5 halves. And since we changed our base to a reciprocal, we can change the sign of our exponent. So now we have 5 halves to the power of 3. So we can see here that we used reciprocal of 2/5 to make our exponent positive. You can also, well, it's a bad arrow. There we go. So we changed our problem. These things are equivalent, so now we can just go ahead and solve for 5/2 to the power of 3. Now we have a positive exponent, so we can go ahead and we can use our power rules. We can use power rule C, which tells us that if we have a fraction, we can distribute our power to our numerator and our denominator. So 5/2 to the power of 3 can be rewritten as 5 to the power of 3 divided by 2 to the power of 3. And this is power rule C. And we want to simplify as much as possible. So we need to simplify our terms here. 5 to the power of 3 is 5 times 5 times 5. 5 times 5 is 25. 25 times 5 is going to give us 125. And then we have 2 to the power of 3. 2 times 2 times 2. So 2 times 2 is 4. And 4 times 2 is 8. So our answer is going to be 125 divided by 8. And this was all possible because we were able to rewrite our expression that had a negative exponent into an expression that has a positive exponent. So once we have that positive exponent, we can use all the power and product rule that we learned in our last section. So that's why we really want to try and rewrite as much as possible so that we have positive exponents. A word of caution, a negative exponent does not indicate a negative number, which we went over earlier. Negative exponents lead to reciprocals, not negative numbers. So if we have something like a to the power of negative n, where we have an example, 3 to the power of negative 2 is equal to 1 divided by 3 to the power of 2, which is just equal to 1 over 9. No negatives. If we have something like negative a to the power of negative 9, then we do have a negative on the outside. So then we'll have a negative 3 to the power of negative 2, which can then be written as negative 1 divided by 3 to the power of 2, which is then negative 1/9, and that will be negative. So a negative exponent does not mean a negative number, but a negative on the outside of our expression will mean a negative number. All right, so then negative to positive rules for exponents. For any non-zero real numbers a and b and any integers m and n, where we have a to the power of negative m divided by b to the power of negative n, can be written as b to the power of positive n divided by a to the power of positive m. This is just like we did in our last example, where we flipped our 2/5 to the negative power of 3 to 5 to the power of 3 divided by 2 to the power of 3. And also, if we have a divided by b to the power of negative m, this is the same as saying b divided by a to the power of m. So even if your exponents are negative and not the same, you can also still flip them. So if we had 2 to the negative 3 divided by 5 to the negative 2, we can also rewrite that as 5 to the positive 2 divided by 2 to the positive 3. So examples would be something like 3 to the power of negative 5 divided by 2 to the power of negative 4. That's equal to 2 to the power of 4 divided by 3 to the power of 5. And if we have 4 divided by 5 to the power of negative 3, we can rewrite that as 5 divided by 4 to the power of 3. And another word of caution, we cannot use the rule a to the power of negative m divided by b to the power of negative n is equal to b to the power of n divided by a to the power of m to change negative exponents to positive exponents if the exponents occur in a sum or a difference of terms. So if we have addition or subtraction going on, we can't use this rule. So as an example, if we have 5 to the power of negative 2 plus 3 to the power of negative 1, all divided by 7 minus 2 to the power of negative 3, written with positive exponents, it's going to simplify down to 1 divided by 5 to the power of 2 plus 1/3 divided by 7 minus 1 divided by 2/3. We can't use our rule as before. We would have to take each individual term and then rewrite that. All right, on to objective 3. We want to use the quotient rule for exponents. So, a helpful example, if we have 6 to the power of 5 divided by 6 to the power of 3, we can extend out our exponents. So 6 to the power of 5 is going to give us 6 times 6 times 6 times 6, where 6 to the power of 3 is going to give us 6 times 6 times 6. So what we see here is that we have 5 factors of 6 on the top and 3 factors of 6 on the bottom. This means that 3 of our 6's on the bottom and 3 of our 6's on the top are all going to cancel out with each other. That's going to leave us with a 6 times 6 divided by 1 is going to be equal to 6 to the power of 2. Which this is going to give us 6 to the power of 5 divided by 6 to the power of 3 is the same thing as saying 6 to the power of 5 minus 3, which is equal to 6 to the power of 2. This example suggests the quotient rule for exponents. So the quotient rule for exponents states that for any non-zero real number a and any integers m and n, a to the power of m divided by a to the power of n is equal to a to the power of m minus n. So we keep the same base and we're subtracting exponents. So once again, we only use this when we have the same base, and then we can just go ahead and subtract our exponents. So our base will stay completely the same while our exponents are now subtracted. So as another example, if we have something like 5 to the power of 8 divided by 5 to the power of 4, that's the same thing as saying 5 to the power of 8 minus 4, which is 5 to the power of 4. Another word of caution. A common error is to write 5 to the power of 8 divided by 5 to the power of 4 as equal to 1 divided by 8 minus 4, which is 1 to the power of 4. So what happened here was that we divided out our base. We did 5 divided by 5, which we say was equal to 1, but that's incorrect. Just like when we use our product rule, we don't multiply our base when they're the same. We don't divide our base when they're the same for our quotient rule either. So if we have 5 to the power of 8 divided by 5 to the power of 4, this is equal to 5 to the power of 8 minus 4, which is equal to 5 to the power of 4. So the quotient must have the same base, which is 5. We can also confirm this by writing out the factors, just like we did in our last problem. So now example 2, we want to simplify using the quotient rule. And we're given our expression here, 3 squared times x to the power of 5 divided by 3 to the power of 4 times x to the power of 3. So we can separate out our like terms here. So we can separate out our 3's and our x's to state that we have 3 to the power of 2 divided by 3 to the power of 4 times x to the power of 5 divided by x to the power of 3. So now we've separated these. Then we can use our quotient rule now, which you can write out as here, quotient rule. And we can write this out using our first quotient rule for our first terms, 3 to the power of 2 divided by 3 to the power of 4. We can write this as 3 to the power of 2 minus 4 times x to the power of 5 minus 3. So 3 to the power of 2 minus 4 is going to leave us with a 3 to the power of negative 2. And x to the power of 5 minus 3 is going to leave us with x to the power of positive 2. And we want to simplify as much as possible. And we don't really want to have negative exponents. So we're going to simplify 3 to the power of negative 2 with its reciprocal with a positive power. So now we'll have 1 divided by 3 to the power of 2 times x to the power of 2, which we can then simplify to 1 over 9 times x to the power of 2. So all right, Very similar in work to the product rule, except now we're just working with dividing and quotients. So here's a summary of all the definitions and rules for exponents. So for all integers m and n and all real numbers a and b for which the following are defined, these definitions and rules hold true. So we know our product rule already. Our zero exponent is just stating that if we have any number raised to the power of 0, our answer will be 1. Our negative exponent, that states that if we have a to the power of negative n is equal to 1 over a to the power of n. Our quotient rule states that if we have a to the power of m divided by a to the power of n, that's the same thing as saying a to the power of n minus n. We already went over our power rules in our last section. And lastly, our negative to positive rules is going to be a to the power of negative m divided by b to the power of negative n is equal to b to the power of n divided by a to the power of m. So just as an example, if we have 2 to the power of negative 4 divided by 5 to the power of negative 3, we can rewrite that as 5 to the power of 3 divided by 2 to the power of 4. Then if we have a divided by b all to the power of negative m, we can rewrite that as b divided by a all to the power of m. So that was our summary. So we're going to do one last problem here. We're going to use combinations of the rules for exponents. So we want to simplify our expression here, which is 4m to the power of negative 3 divided by 3m to the power of negative 4. So we have negative exponents in both cases here, and we need to distribute these exponents as well. Let's go ahead, and the first thing we want to do is we want to use our negative to positive rules. So we're going to say negative to positive rule. Now we're going to say that A is 4m and B is 3m. So then we can rewrite our expression as a to the power of negative 3 divided by b to the power of negative 4, which using our negative to positive rule, we can write as b to the power of 4 divided by a to the power of 3. And then to actually move this down a little bit here, more relevant there. So now we have this new expression and we can replace a and b with 4m and 3m. So what we really have here is 3m to the power of 3, to the power of 4, divided by 4m to the power of 3. And now we can go ahead and distribute our exponent. So when we distribute our exponent, we're going to have 3 to the power of 4 times m to the power of 4 divided by 4 to the power of 3 times m to the power of 3. And in this case, we use our power rule B. And now we see that we have m's in our numerator and our denominator. 3 to the power of 4 and 4 to the power of 3, they have different bases and exponents, so those numbers are going to have to be solved on their own. But we can separate out our expression a little bit here. So we can write 3 to the power of 4 divided by 4 to the power of 3 times m to the power of 4 divided by m to the power of 3, which we can then rewrite as 3 to the power of 4 divided by 4 to the power of 3 times m to the power of 4 minus 3. And this is using our quotient rule. So now we have 3 to the power of 4 divided by 4 to the power of 3 times m. This is technically m to the power of 1, but we normally don't write the 1, so we just have 3 to the power of 4 divided by 4 to the power of 3 times m. Which we now have constants with exponents. So we can go ahead and solve these as well. 3 to the power of 4. If we have 3 times 3, that's going to be 9. 9 times 3 is 27, and 27 times 3 is going to give us 81. Then we have 4 to the power of 3, where if we have 4 times 4 is 16, and 16 times 4 is going to be 64. And this is all times m. And this is our most simplified expression. So we see here in this problem, we use 3 different rules for exponents to simplify our expression as much as possible. So you can use any different combination of our rules that we have for exponents. You can even use them multiple times or the same ones multiple times if you need to. So that concludes section 5.2, and I'll see you all again in section 5.3.